So I'm going to talk about obfuscation. My talk title is Obfuscation from Noisy Linear Functional Encryption, and we'll discuss what that means. Okay, so uh, first let's just talk about what obfuscation is. So let's start with an intuitive notion. Let's say that you're a smart student at IIT Madras and you figure out a better algorithm to factor numbers. Now you could write a paper and win the best paper award at crypto, or you might be more enterprising than me at least and decide that you want to keep the algorithm secret and sell functionality. So what you'd like to do here is sort of take your code and input it into some kind of a magical black box or yellow box in my case. And what should pop out is an obfuscated code. So what this means is that this code which has come out should still produce the correct output, but it should be impossible to reverse engineer. So this is our intuitive notion of an obfuscator. And just a little bit more formally, what we're hoping to do is compile a circuit C into a different one C hat that preserves functionality, but is unintelligible. Okay, so it's somehow resistant to reverse engineering. And what do we mean by resistant to reverse engineering? So this is an obfuscator, and our notion of security is going to be what's known as indistinguishability obfuscation. Okay, so this was a notion defined by Barak et al. And it says that it should be hard to figure out which one of two equivalent circuits, C1 or C2, is obfuscated. Okay, so let's be a little bit careful here. What do we mean by equivalent circuits? So two circuits are equivalent if they have the same size and the same truth table. Okay, and what you want is that the obfuscated version of C1 should be indistinguishable from the obfuscated version of C2. So now a moment's thought will tell you that this is a trivial problem to solve if efficiency is not a concern. And why is that? Because, well, if the truth tables are the same, then you can fix a canonical circuit for every truth table and you can just output that. But our goal in this talk and in this line of work is to find an efficient compiler IO. Okay. So before we proceed, it's important to ask, why do we care about this, right? So it seems, at least at first glance, like a reasonably, a sort of useless definition. If we already know that both circuits are equivalent, then does it really matter what's the particular representation of the circuit? And it's not clear off the bat what applications there are to this notion. But the fantastic thing is that a kind of theorem that has emerged from the first candidate IO that we saw in 2013 is that IO is actually almost crypto complete. Okay, so what do I mean by that? So IO, since its first candidate construction in a breakthrough work by Garg et al. In 2013, has seen just an amazing number of applications. And many of these applications are things that we really don't know how to do any other way. So it really, opens up this completely fantastic set of applications, and it's even warranted its own name. So, this land where all these amazing new applications live is now known as Obfustopia. Okay, so hopefully you will just believe me. I mean, you can go and take a look at the literature. The reason I don't have citations on the previous slide is that I think it's impossible to get all the citations for this. There's just been so much work, right? So hopefully you will believe me that this is a very important notion. And the pressing question, therefore, before us is, does IO exist? Okay, so does IO exist? And I cannot give you a straight answer to this question. It really depends on what you mean by exist. So it kind of, I can give you a quantum answer. So it exists and doesn't exist. Why? Because it exists because we do have some constructions, and it still doesn't fully exist because we don't fully understand whether it's secure. Okay, so let's talk about these constructions. Now, constructions of IO can be categorized into these two broad branches. The first one is direct constructions, and the second one is bootstrapping based constructions. So direct constructions are all based on multilinear maps. We'll talk in a minute about what that is. And they more or less use the same template in all works. So the underlying multilinear map may vary, but more or less the sort of recipe for constructing the IO is roughly the same. And these direct constructions have gone through a tumultuous history, to say the least. I mean, there have been candidates and then attacks on those candidates and then fixes and then more attacks. And, the cycle has kind of kept on. And it's been hard in general to understand security. Okay, and then the second type of construction that we have is bootstrapping based constructions. So now in my talk, I'm going to primarily focus on bootstrapping based constructions. But before that, I'd like to say a few words about these direct constructions. Okay, so as I told you, they're all based on multilinear maps. So let me tell you what those are. Before I tell you about multilinear maps, let's do a quick recap on bilinear maps, which are a tremendously useful object in cryptography. Okay, so here's the definition of a cryptographic bilinear map. So we have two groups G1 and G2 of some prime order P, and they have these generators little g1 and little g2, and a bilinear map E that takes G1 cross G1 to G2, such that for all AB in ZP star, E of G1 to the A, G1 to the B gives you G2 to the AB. So what is this really letting you do? What it's letting you do is encode two elements obliviously. So A and B are two elements that I'm encoding here. They're going to be hidden because of the hardness of discrete log, right? Because they're sitting in the exponent. And this map E is letting me multiply these two elements without knowing these elements, right? So I apply the map and I get G2 to the AB. The hardness that I want here is called the bilinear Diffie-Hellman problem. I'm not going to define it because we're not going to use it, but let me just give you a flavor. So what this hard problem says is that, well, as we saw, you can compute degree 2 polynomials in the exponent. So I showed you that the map lets you multiply, and obviously you can add, right? The hard problem says that any degree 3 computation should be indistinguishable from random. So if I have G2 to the ABC, right, then that should be indistinguishable from a random element. All right, so we have for these bilinear maps efficient instantiations from Weyl and Tate pairings over elliptic curves. And these have just been enormously useful in cryptography. So for instance, they gave the first construction of identity-based encryption, right? So they're very, very useful. And now let's move on to multilinear maps. So as you can imagine, this is a generalization of the notion that I showed you before. So now instead of two maps, or sorry, instead of two groups, I now have n groups, G1 to the Gn. And I have a family of maps, as you can see here. So now I can take any Gi cross Gk to Gi plus k, right? And the same bilinearity property holds for the map. The difference, of course, is that now when I land up in Gi plus k, I can keep going. So I don't have to stop, right? So I can do more than one multiplication. I can compute higher degree polynomials in the exponent. And the hardness that I'd like is that, well, obviously discrete log should be hard. And hopefully there's some generalization of bilinear DH. So you should not be able to distinguish a product of n plus 1 elements from random. All right, so so that's kind of the hard problem that we have. So a little bit about multilinear maps. Applications of multilinear maps were described by Bonnet and Silverberg as early as 2003. But in general, there's been pessimism about their existence in the realm of algebraic geometry. So I should say that they exist, but efficiently computable ones, we do not have them. All right. Now, in 2013, there was this remarkable work by Garg, Gentry, and Halevi that gave the first candidate construction of these multilinear maps. And this was based on ideal lattices using ideas inspired from the Entro crypto system. And these are immensely useful. So as I already told you, they can be used to build IO and also a whole host of other things. The first construction of IO from multilinear maps needs maps of polynomial degree. Okay, so I'll not talk much more about multilinear maps. Yilei will talk about them more tomorrow. So now let's look at these bootstrapping based constructions. Okay, so here the sort of philosophy is reduce, reduce, reduce. Reduce everything as much as you can. Reduce the functionality that you need to construct IO. Reduce the assumptions as much as you can. And there has been a lot of progress in this area. So let's see. So as I already told you, when I want to use multilinear maps to build IO, the first constructions were using multilinear maps of polynomial degree. Then, there was some work that showed us how to simplify functionality. And this was quite surprising at the time. So you can make do only with constant degree multilinear maps, but the assumptions that you're using are still messy. Then there was another very nice work by Lin and Vaikunthanathan, which shows that you can use constant degree multilinear maps with nice assumptions. So no longer messy. And then there was more work that shows that this constant can actually be reduced quite a lot. So in the previous works, it was something like 30. And now it can be reduced to something as small as 3. And you have nice assumptions. So this is fantastic because, degree 3, I mean, that's very, very close to degree 2. We already have degree 2 and we have nice assumptions. So, that's really great news. But pretty soon this excitement sort of gives way to depression because we don't actually have these degree 3 multilinear maps, right? And where is this degree 3 barrier coming from? So just at a very, very high level, we'll see more of this in the rest of the talk, but I just want to give you a flavor. Essentially, having reduced everything as much as possible, you're going to need to somehow generate randomness obliviously. So you want to somehow compute, randomness within the multilinear map. And this needs a computation of degree at least 3. This was demonstrated by some lower bounds. Okay, so here we have this fantastic IO land, which needs degree 3 or more maps. And we know how to get degree 2 maps from elliptic curve groups. And what we'd really like to do is bridge these two lands, because our degree 2 land is already quite cool, but now that we've seen applications of IO, we feel more greedy. So we'd really like to get to this degree 3 land. And this is a big open problem. Okay, so here's my first open problem for you. It would be a huge breakthrough if we could construct a secure multilinear map of degree greater than 2 from algebraic geometry, for instance. Okay, all right. So that's where, we were with these multilinear map-based constructions. A natural question to ask is, can we base IO on anything else? And it turns out, yes, there's another primitive, that we can use in order to construct IO. And that's the primitive of functional encryption. I'm going to define it in a second. But now you also need this functional encryption scheme to support computation of degree at least 3. And this could be good news, except that constructions of degree 3 functional encryption were themselves based on multilinear maps. Okay, so it seems like we're kind of back where we started, but maybe not quite. So, we're only 15 minutes into the talk. So, there's more to come. Let me tell you what functional encryption is, and then we'll see what we can do with it. So functional encryption is this powerful primitive. It's a generalization of public key encryption. And here's the idea. So you have a setup algorithm. It outputs a master public key and a master secret key. The encrypt algorithm is just like public key encryption. It takes some input X and produces a ciphertext. The main difference of functional encryption from public key encryption is the key generation algorithm, which now takes as input this master secret key and some function, which we'll think of as a circuit, and it's going to output a secret key corresponding to this circuit. And now, in order to decrypt, I'm going to put together the secret key and the ciphertext, and what it gives me is f of x and nothing else. Okay, so remember that public key encryption is an all or nothing primitive. If you have the secret key, you have the whole x, or you have nothing. But functional encryption lets you get this fine-grained information. So you can actually compute functions on X and nothing else. And the notion of security that we're going to need here is the following. So we'll play a game between a challenger and an adversary, where the adversary outputs 2 challenge messages and receives an encryption of random 1. And then the adversary gets the public key and can make requests to the challenger to receive keys corresponding to different functions. It will get those keys, right? And it can make, let's say, Q such queries. Now here, note that it should be the case that f of x0 is equal to f of x1 for any f that you queried. And why is that? Because, well, functional encryption lets you compute f of x given the secret key and the ciphertext. So obviously, if the function itself distinguishes the 2 messages, then you have no hope of security. So we're going to have this requirement. And then finally, the attacker outputs a bit B and wins if the bit B that it output is the same as the one chosen by the challenger. Okay, so I want to quickly remark that this definition is really the same as the semantic security definition for public key encryption, except that now the attacker gets access to these secret keys, right? And that makes sense, because in a functional encryption scheme, you can have these partial decryption keys. All right, so now in order to imply IO, we're going to need that the ciphertext size of this functional encryption scheme should be sublinear in Q. So if the scheme supports Q key requests, I need the ciphertext size to be sublinear in Q. Okay, so this is our succinctness requirement. All right, so IO from functional encryption, what do we have here? So there's been a long sequence of works, and that culminated in needing a functional encryption scheme that supports computation of constant degree polynomials. Okay, so as I told you before, all right. And then there was some works that showed that actually you don't even need public key functional encryption, symmetric key suffices. Okay, so in this talk, I'm going to show you a new abstraction. So previously we had functional encryption for degree at least 3 polynomials. In this talk, I'm going to show you a weaker notion of functional encryption, which I'm going to call noisy linear functional encryption. And I'll show you that this actually suffices to give you IO. Okay, and obviously for this to be of any use to us, this should be weaker than, FE for degree 3. So the theorem that we have is that a sort of special kind of fully homomorphic encryption scheme that can be constructed from LWE or ring LWE plus noisy linear FE satisfying the usual notion of security implies IO. Okay, so this is what we're going to have. Now, in this talk, I'm not at all going to talk about this special FHE scheme. I'm just going to tell you about the noisy linear FE. I refer you to the paper for this other part. Okay, so noisy linear FE to IO, what are we going to get? So before I even define it, let me lay out the landscape about where we are going, right? So noisy linear FE using these special FHE encodings can be bootstrapped to give FE for P with the required succinctness. And this, by the work of AJ and BV, implies IO. And noisy linear FE, well, there were different ways of constructing it. Some of them were broken. Right now, what stands is broadly the following two paths. So path number one is that you can use the so-called notion of partially hiding functional encryption, which can be constructed from bilinear maps and strengthening of LWE. This can be used to instantiate noisy linear FE, and this is actually formal. So I can construct a noisy linear FE scheme using a partially hiding functional encryption scheme. Okay, and Rachel, Ayush, and Amit will talk about this. Or I need not use bilinear maps at all, and I can just give you a direct construction for noisy linear FE, and that's going to be the rest of my talk. All right. Okay, so what is this noisy linear functional encryption scheme? So before we think about noisy linear FE, let's at least look at what is linear FE. Okay, so let's think of two vectors, x and y, that live in some ring R. And now I'm going to encrypt x just as before. Yes?
Quick question. So will you define this special FHE in this talk, or
No,
it's necessary?
it's not, I mean, it's not necessary for this talk because I'm not showing you the bootstrapping. It's a fully homomorphic encryption scheme that has certain extra structural properties. So yeah, that's all I'm going to say. Think of it as a kind of FE friendliness.
Okay.
Yeah. Any more questions? So the reason that I did not want to dwell too much upon that part is because there are ways of building it just from LWE and ring LWE. So, there's nothing there that needs to be improved, so to speak, in order to get IO. So all the mess is in this noisy linear FE. So that's why I decided to focus on that. Okay. Yeah. So key generation is going to be as before, but now your circuit is nothing but a vector y. So you'll get some SKY. And when you put them together, you should just get X in a product y. Okay. And this is a pretty sort of basic, primitive, a very useful tool to have in your toolkit. It also admits very sort of simple, efficient, and clean instantiations. It can be constructed, for instance, from DDH, LWE, and quadratic residuosity. So now what is noisy linear functional encryption? Well, I just want to add noise to the output. So, my message is still X, my function vector is still Y. I want the decryptor to get X in a product Y plus some noise. And, maybe you're unhappy with the hand waving I'm doing. I mean, where does this noise come from? What security properties does it need to satisfy? If I need to add noise, don't I need to generate it? If I need to generate it, isn't it like generating randomness? And isn't that high degree computation? Am I going in circles? Well, I'm going to address these questions as we go on in this talk. Questions? Okay. All right, so noisy linear functional encryption.
So actually a question. Could you instead define this as X in a product, rounded X in a product Y? I mean, I know that that would give you a high degree and so forth, but you could do that as well.
Yes.
Okay.
Yes. So I should say that we would need to rework the bootstrapping step. But, I don't think that's going to be an issue. Yeah. Okay, so here we have it as before, right? So ciphertext for X, keygen for Y, decryption X in a product Y plus noise. And there are at least two things that this noise needs to satisfy. So it needs to be bounded. Um, let's say that is bounded above by some bound. Actually, you can weaken this condition, like you can look at the distribution of noise more carefully rather than just giving an upper bound on the size. But for the purpose of this talk, I'll just think of it as being bounded, and I'll just use that. And you would like it to satisfy some kind of weak pseudo randomness, which we'll talk about. And the notion of security now that we need, it's similar to before, but there are some important differences. So first of all, I'm going to only look at the symmetric key setting. So now the adversary is also asking the challenger for ciphertext requests. Okay, and as usual, it's asking for key requests. Now the condition that we have on the adversary is that it should be that the difference of inner products of x0i and x1i with any key y, this difference should be bounded by some quantity. Okay, so again, you can be more careful and think of distributions rather than a bound, but again, for simplicity, we'll just assume this. Now just note that in a standard notion of linear FE, you would have this b to be 0, right? Or it should be, the difference should be equal to 0, so the inner products should be exactly equal. So noisy linear FE is saying that, well, I can request for keys that differentiate the outputs a little bit, but the scheme should somehow add noise and hide that difference. Okay, so it should still be hard for the attacker to guess which ciphertext it receives, and the winning condition is the same. The succinctness condition is the same. So if the attacker asks for Q keys, I need that the ciphertext size should be sublinear in Q. Okay, so let's look at this all important question of where is this noise coming from? Okay, so at a high level, we're going to use a PRG to compute this noise. And recall what is a PRG. So it's a basic object in cryptography, which takes a short random seed and stretches it into a longer pseudo-random output. Okay, so I'm going to want to represent this G as a polynomial, and I want to use my FE to compute G of seed and add it to the output. Okay, so it's already computing X inner product Y. I want it to additionally add G of seed to this output. So the key new observation that I'd like to make here is really sort of old, grandmom advice, which is that, well, if you cannot have what you want, you should learn to want what you have. Repurposed in our context, what this is saying is, if you cannot compute what you can use, you should learn to use what you can compute. So what am I trying to get at? I want to be able to relax the requirement on correctness. Okay, so I told you I want to use PRG to compute this noise, right? So that would make the scheme look like this. But as we've already discussed, I mean, this PRG computation is going to need degree at least 3 if I want to compute it exactly, right? So I did not make any progress by just insisting that you compute G of C. If I do that, then, we're not doing anything that wasn't done before. The new observation, as I tried to intuit in the previous 2 slides, is that the requirement on correctness now is actually much weaker, right? So only X inner product Y needs to be correct. The precise value of G of seed is not important because its only purpose is to add some perturbation, right? And satisfy some mild statistical property. It doesn't really matter what its precise value is. In particular, if my decryption, instead of outputting X inner product Y plus G of seed, if it somehow outputs some, XY plus G prime seed prime, for some perturbed G prime and seed prime, it's all right. It's perfectly okay, because this noise thing does not really participate in correctness. It only participates in security. So far, we've assumed that the polynomial is a PRG and insisted on computing it exactly. And here what we're doing is we're saying, well, compute whatever you can compute and check if it can satisfy the statistical properties that you need. Okay, and this turns out to be powerful because it permits new direct constructions. So what we show is that the linear functional encryption scheme from LWE can be extended to noisy linear functional encryption using new hardness conjectures on lattices, which are very different from multilinear map-based assumptions. These may be more robust, they may be post-quantum. In any case, they're much simpler to analyze than mmap based direct constructions. And intuitively, this is because the part of the IO construction that's using heuristics is kind of minimized quite a lot, right? So I'm not building a direct IO scheme. I'm just building like a little component. And having built this component, the rest of the bootstrapping all the way from noisy linear FE to IO is all provable security based on LWE. And what's cool is that this yields the first construction of IO using no maps at all. So no multilinear maps, not even any bilinear maps, pure lattices, which makes me happy. Of course, we have to hope that it's secure. We'll talk about that. All right, so let's look at the construction. So before that, are there any questions?
There is one question you can look at in the screen.
This PRG is said to be weak. In what sense? Okay, so answer live. Yeah. So this PRG is weak in the sense that I don't actually need it to produce an output that is indistinguishable from random. What I need is that I need this PRG to satisfy some kind of a flooding, a computational flooding property. So let's say that I have some random variable x, okay? I need that x plus y should be indistinguishable from y, where y is the output of the PRG. And x intuitively is that difference in the decryption output. So if you remember when I showed you the security game of noisy linear FE, I said that the two challenge messages can decrypt to slightly different values. So if I think of the difference between these decryptions as being x, then I need that this y should sort of computationally flood x. And actually it can be weakened even more. So I need that x plus y is only 1 over poly distinguishable from y. So Rachel and Ayush will likely, I'm sure, will talk much more about this. Okay, for my talk, this is all I want to say. All right.
Shweta,
yeah.
Sorry, another question. So just a clarification about your answer to Vinod's question about rounding instead of adding noise. So why is rounding bad? Because it's high degree?
Yes.
Okay, thanks. Okay.
Yes.
Thank you.
Okay, so construction. So good. So it's going to be based on the ring learning with errors problem, which, for all those who attended the workshops at Simon's, we've sort of seen this again and again. So the ring learning with errors problem says that it should be hard to distinguish noisy inner products from uniform over a ring with suitably chosen noise. Okay. All right. And now let's quickly recap Regev's public key encryption scheme, or one variant of it, and we're going to repurpose that step by step. So first of all, recall that from the SIS problem, it should be hard to find a short vector E such that A inner product E is U for some fixed public U. Okay, so using this, I'm going to set my secret key as this short vector E, and I'm going to set my public key as A and U. And in order to encrypt, here's what I do. So I sample a ring element S, and I compute C0 as AS plus 2 times noise. So I'm going to use this LSB encoding, as they say. Okay, so C0 is this, and C1 is US plus 2 times noise plus my bit X. Okay, and now decryption is sort of very natural. So I mean, I have AS plus noise, US plus noise plus X, and my secret key is E, and the relation that I have is that A in a product E is U. So I mean, there's only one thing you can do. You can take E in a product C0, and that will recover for you the U times S term, right? It will also create an inner product of the error with E, but because our E is small, so intuitively this error will not hurt us too much. So when I subtract these two, I'm going to get X plus 2 times error, and then I can compute mod 2 to recover X. Okay, so this is the version of regev's PKE that I will use for my talk. Now let's, yeah, I already said this. So this is small if E is small, and the ciphertext is pseudo-random by ring LWE. So now let's use this to construct linear functional encryption, okay? So now I want to encode a vector X. So what's the natural thing to do? Well, repeat it L times, okay? So now I have L elements U1 to UL, and correspondingly L short E's, such that AEI is UI. Okay, I'm going to encrypt just like before. So my C0 is exactly the same. My C1 is also exactly the same, except that, you know, I encrypt X coordinate by coordinate. The key for a given vector Y is going to be the inner product of, or, you know, the matrix vector product of Y with this matrix of E's. So summation Yi EI. And now why does decryption work? Okay, so if I take this key, and as in the regev scheme, if I, you know, multiply it with C0, then I'm going to get a summation Yi UIS plus noise. And now I can also take Y transpose C1 and, you know, similarly get this summation Yi UIS term. And this also gives me X inner product Y, right? So now when I subtract these, what I end up with is X inner product Y plus noise. Okay, so I can round off this noise and recover X inner product Y. Okay, but wait a minute. I mean, decryption, as I just showed you, is already giving me X inner product Y plus noise. And I just told you that I can round off this noise and recover X inner product Y. But I mean, I thought we were going for noisy linear FE. So why does this not do it? Well, as you can guess, it's because this noise is not pseudo-random. Okay, so in particular, this noise can be fully determined after sufficiently many key requests. Okay, so let's see how to add noise. Okay, so here's a sort of trivial starting point idea. I know how to compute X inner product Y. Let's say I add a dummy coordinate. Okay, so I give you a fresh encoding of noise. So my X L plus 1 is noise, Y L plus 1 is just 1. And now inner product is X, you know, X Y plus noise, which is what I wanted. I can repeat this Q times once for each key request. And this is a trivial solution, which unsurprisingly does not work. It will satisfy security, but it violates the succinctness property that I told you was needed to imply IO, right? So now my ciphertext size is going to grow with the number of key requests, because for each key, I'm kind of hard coding this noise term. So this is bad. All right, so this is not going to work for us. What I'd really like to do is I'd like to somehow compute encodings of noise on the fly. So this, you know, dummy way, yeah.
So if you go back, you know, you're saying you need to add one coordinate for each key request with a fresh noise in it. That's
a trivial, yeah, as a trivial solution, which would satisfy the security you want. So if the succinctness were not a problem, you could do this. And actually, this was the starting point idea of this work. That, I mean, you can do this, and now I want to somehow make it succinct. So I want to compute these encodings of noise on the fly. And what's this encoding of noise? I mean, it's just a regev encoding. It's just an LWE sample. It's something like US plus noise, where now this, let's say US plus noise prime, right? So now this noise prime is my new message, because I want to compute an encoding of noise, right? So just think of it as a regev encoding of, or a LWE encoding of noise. The question is, can I compute this on the fly? So yeah, I mean, just to remind us again, in general, you need a high degree polynomial to compute this, and we don't have functional encryption to support this. So obviously what we're going to try to do here is somehow leverage this approximate computation idea. So the question is, can I do something better if I don't care about the exact value? And here, enter entrue on a red carpet. So now let's see what we can do. Here's an idea. Okay, so let me now think of two rings, RP1 and RP2, as R mod P1R and R mod P2R. And as I told you, I want to compute an encoding of noise that roughly looks like this. So by the way, I mean, this distinction of P1 error and noise, I'm just making it for the purpose of, us really seeing this noise as a message. Okay, it's not going to be super important in the end, but let's just stick with this description. So, yeah, so the noise here is the message, right? And what do we do now? So I'm going to do the following. So I'm going to first generate a bunch of entrue samples, or entrue like samples. I'll sample some short elements F1I and F2I, for some polynomial I. So I is some the range of I is some polynomial. And I also sample G1 and G2 from a discrete Gaussian over the ring. And I compute these entrue like samples. So H1I is F1I over G1, and H2J is F2J over G2. Now note that unlike entrue, I'm actually reusing the denominators here. And I'm going to assume that these look random. Now I want to say a couple of words about this assumption. So first of all, this assumption is also implicitly made in multilinear map-based constructions, and it's never been a source of insecurity. It's also been studied in Pikert's survey on lattice, a decade of lattice-based cryptography. So he studies this problem in section 4.4.4. So, you're welcome to look at that. So this is going to be an assumption that we make, that these look like random. Okay, and now what we're going to do is we're going to treat these sort of,
can you put the assumption back up again? Just sort of want to slow down a little bit and want to look at it. Oh, I see. So you're saying each, all the H1Js, they have the same denominator.
That's right. Yeah. So you can think of it as a sort of bipartite graph, if you will. Okay. So you have a bunch of H1s and a bunch of H2s. Okay. And all the vertices on one side share the same denominator.
Okay, I see.
Hey, Shweta, can you remind us? Oh, sorry.
Oh, so is it my phone?
No, it's mine. Hey, Shweta, can you remind us? So the entrue encryption. Just remind us of how that works. Where did the F over G come from?
Okay, so the way we do entrue encryption is we have just an H, Okay, so let's say that H is F over G. And now your secret key will be G and the public key will be H. So N-true is assuming that this looks like random. And now to encrypt, you do HS plus noise plus message. Okay, so again, let's think of HS plus 2 times noise plus message. And let's also think of H as 2F over G, just
So
for
the
simplicity.
but in terms of the roles, so the H's are the public key.
That's exactly right. Yes.
The public keys. So you're sampling a bunch of public keys, except for all these public keys, the G1 and G2 are the same.
Yeah.
Which makes it sort of okay. So that's the weakening of the assumption. Okay.
A strength, a strengthening of the assumption. I mean, it's a worse assumption.
Right. So weakening the not the assumption, but the security. Got it. Okay.
Yeah. Right.
Thanks,
Yeah.
that's happening. So right. Okay. Good.
So would you like me to finish the description?
No. I was just trying to remember what was the role of H here.
Right.
And the fact the way to think about it is if it's different.
Yeah.
Okay.
It's, I mean, yeah, thanks for bringing that up, because also that's exactly how we're going to use it in our scheme.
Mm-hmm. Okay.
Okay. So, yeah. So, yeah, we're going to have these, as part of the key. Actually, we're only going to construct a symmetric key system. So, but they could be public. So it doesn't hurt to have these public, but these are going to be part of the key. Okay, and now I want to compute, an encoding of noise, which looks like this, right? So it looks like some HS plus noise plus the message, which in this case is also noise. Now here is the main idea. Okay, I'm going to sample my error in a structured way. So my error is now not going to be from a discrete Gaussian over the whole ring. It's actually going to live in a principal ideal of the ring, and this principal ideal is going to be hidden. So I'm going to sample these errors from a discrete Gaussian from this structured ideal. And now why am I doing this? So recall, this is our H1I and H2J, right? And now note that this error, actually, if I just look at it algebraically, forgetting about the distribution for a second. So if I look at it algebraically, this error has this, G1 or G2 sort of built into it. Okay, so in particular, when I multiply this error, like when I multiply E2I with H1J, then the G1 term sort of cancels out. Okay, so what this gives me is that, as I was saying, if I think of, this bipartite graph with all the H1s and E1s living on one side and the H2s and E2s living on the other side, then all the H1s on this side sort of annihilate with the errors on the other side. Does that make sense? So the cross terms are now going to be small. Okay, and this is sort of the main new idea here. So we've shown that, these errors are going to be, these errors, when I multiply them with the large label of the LWE sample, which is going to be H1I or H2J, I'm going to end up with something small. So now what I can do is, if I have these LWE samples with sort of the structured noise and the N-true labels, then when I multiply them, what happens is that the cross terms do not blow up. So this is a way of, managing our cross terms. And now when I multiply them, then I get a term that looks like this. So this is very close to the green box that we have above, right? So it's, there's some H which is publicly computable, or in any case computable by the key generator. There's a secret, it should be T1 times T2, sorry, here there's a typo here. So the secret is now T1 times T2. We can think of that as S. And there is some noise. And now this noise is sort of this funny looking noise, but we're going to study why this noise might be okay. Are there any questions? All right. So
sorry, I have a question.
Yeah.
It's also asked in Q&A. So in the previous, like the intro with the same denominator assumption, how large is the W? Meaning how much?
Yeah, just think of it as a security parameter.
So what's the, okay, thank you.
Yeah. And actually, now that you ask that, so the reason we have, the security parameter number of these is that I don't just want to compute this one product. So I'm going to do many of these products and I'm going to add them up. So what this does is that, let's look at the sort of quadratic term in this in this noise here. So it's G1, G2 times this eta 1i, eta 2j, right? So now this, if I ignore the P1, this lives in this ideal G1, G2, and this ideal should be hidden. So I don't want the adversary, when she decrypts, I don't want her to recover all the noise terms living in the same principal ideal. So what I'm going to do is I'm going to do this many, many times and add it up, right? And this will this will randomize the G1, G2. So I'm going to have many copies of this and I'm going to add them all up. So the noise will then get spread out over the ideal.
So may I also ask, in this question, is it enough to recover the ideal to break the scheme? Or?
If there were only one ideal, then yes. So what I'm showing you is a simplified version of the scheme. As I discuss this later, in the real scheme that we have, there's not just one G1 and G2. So right now what I showed you is just this one bipartite graph where there's a single G1 and a single G2. But we also repeat that security parameter number of times. So now there are, there are lambda copies of G1, G2. All of them are different. Okay, and now when I do these multiplications and then I add up these encodings. So the noise term that results is going to roughly be like a summation of, G1i, G2j times new randomness. So this is, if you didn't have the, G1, G2s at all, then this would be sort of noise that's distributed like in the regular ring LWE case. You do have now these G1s and G2s, but to mitigate the effect that it lives in a principal ideal, if I only do it once, like if I only have one bipartite graph, then there's a single principal ideal G1 times G2. But if I have lambda many of them, then I have the adversary is actually recovering a noise which now is a summation of noise terms that live in these ideals. So it, again, the noise spreads out over the whole ring. So if you could recover, so this is no longer the principal ideal problem. So even quantumly, we don't know how to solve it. So if you could recover these secret elements, then it would be a problem for security, but we don't know how to do it.
Okay.
Yeah, so the key idea, as I said, the key first idea in this construction is that the noise lives in an ideal that cancels the large term in a ring LWE sample. And the nice thing here is that there's no need to stop at 2. So, with all lattice-based constructions, if you can do degree 2, you can, do more. And that's also the case here. So there's no restriction of map or anything. You can kind of keep going. Okay, so the theorem is that it's easy to make noise. The description that I gave you is oversimplified. I also described one other idea that we use. There are also more ideas. So for instance, remember what's our secret key? So our secret key is a short vector that maps some matrix to another vector, right? Or some vector to some matrix to another vector. Now, what we can also do is that this short vector, which is the key, can also do an approximate mapping. So that's a way for even the key to add noise into the decryption equation. So there are multiple ways in which you can add to this noise term that the adversary recovers. Okay. So what about security? So now this is, of course, the most important question. And sort of roughly speaking, there are two axes on which we need to think. The first is just the semantic security of the encoding. So these encodings are sort of non-standard encodings. They're using this, n-true label, and they're using the structured noise. Are they secure? That's one question. The second thing is that I'm using these non-standard encodings to compute these encodings of noise on the fly, which will finally be plugged into my linear FE scheme, right? And then the adversary is going to actually learn X inner product Y plus noise, where noise is the stuff that I generated, right? So does this noise serve the weak pseudo-randomness property that it needs to serve? So these are sort of the two questions that we have. And let me tell you a little bit about security. So I see that I'm running out of time, so I'll maybe just say a few words. So in the first work from last Eurocrypt, where we introduced this scheme, we did some analysis. And we tried to do a proof, but it doesn't quite work out. I mean, we get a proof from a really clumsy assumption in a very weak security game where the attacker only gets a single ciphertext. And security, unfortunately, is based on the inability to find attacks. This is, a bit unsurprising given lattice-based proof techniques. But the good news is that it's still a much simpler system to analyze than previous direct constructions. It minimizes the part that depends on heuristics. It uses no maps and has a different design template, and it has a chance of being post-quantum. So in a follow-up work with Alice, we did much more rigorous cryptanalysis, and we did find two problems with the scheme, which we could fix. So these two problems, in my view, even though they're sort of serious problems in that they break the scheme, in my view, they're not fundamental problems. So, the fix is not very complicated, and the scheme does not change very much with the fix. We also suggest concrete parameters. We develop new cryptanalytic techniques, and we feel that the security is on a much firmer footing after this work. So our hope is that this inspires new candidates. Okay, so Vinod, how much more time can I take?
So formally, we are kind of out of time. So,
yeah.
So maybe this is a good time to sort of stop and ask questions, so we can sort of keep
All
up.
right, sounds good. So let me just wrap up then. Yeah, so I won't have time to go into the attacks or the fix. So let me just tell you that the first attack had to do with the commutativity of these polynomials. So in some sense, the way we set it up, the structured noise annihilates the large term not only in its own ciphertext, but also in other ciphertexts. So this ends up being a problem, and you can fix this by making it non-commutative. And the second attack, I want to just say a couple of words about it. So yeah, like if you, or maybe I'll show you the other slide which has the noise term. Yeah, so yeah, this is what the noise term looks like for degree 2. Of course, our final noise will be of higher degree than 2. But in the original scheme, I had this tower of moduli. And what this tower of moduli was doing is it was sort of inadvertently creating these layers between the noise. So the noise, as you can see, is like this large complex polynomial equation, which is good. That's what we want, right? And the focus had been on sort of getting like a high degree term. But what ends up happening is because of these, public moduli that separate these noise terms, you can actually recover them separately. And then there's a kind of a rank attack that can be launched. But this can be fixed by not having these different moduli. So I feel that this is, yeah, so there's a natural way to fix it. You don't need to have these different moduli. So you can go back to an error term which looks, pretty, it looks like a high degree polynomial equation spread, as I said. So each term lives in one ideal, but it's going to be a linear combination over many ideals. So if you can see here, there's, G1L and G2L. So there are many of these L's, right? There are security parameter, many of them. So it's also this high degree polynomial, which is spread out over the whole ring. And if you didn't have these secret ideals, as I already said before, this would be a good noise term with no problems. It would just be like a Goldreich PRG noise term. But we do have these secret ideals. We mitigate their effect by having many of them and just adding them all up. So sort of thereby not letting the adversary separate them and leverage any structure. So yeah, this is the final slide. As I said, we did find a couple of problems in the scheme, but in my view, it's not a fundamental vulnerability. The scheme that we have can help us to compute super polynomially large noise. So you can, flood the noise in the original scheme easily. And it's a new design methodology, and it's my hope that we'll get more candidates for the subject. So what's open is proof from simple assumptions. From purely LWE, this seems quite difficult, but I cannot say that it's impossible. There is, by the way, some negative evidence. There are some lower bounds that show that IO cannot be constructed from sort of all or nothing primitives or assumptions like LWE. But I won't go into that now. We'd like to see more candidates, and we'd also like to see better efficiency. So if all of this, works out, if everything is secure, it's still a monster. So, it's nowhere in a place where it can be implemented at this moment. So it's also good to have schemes that are more efficient. Thank you.
Indeed. So we have two questions in the Q&A.
Okay.
Shweta, if you can take a look.
Yeah, I can take a look. Yeah. Can noises for two different computations be correlated? Would this be a problem? So this is a very good question. So the noises from two different computations can indeed be correlated, but this correlation is inherent to a PRG, isn't it? So if I have a PRG, it only has a short seed, but I'm still generating a long output. So obviously, sort of each output noise is correlated, right? All the output noises are correlated. And that's also going to be the case here. But what we do here is no worse than what's already happening in a PRG. Second question, FE plus noise. Yeah.
So yeah, you should answer this, but we should kind of keep on time. So, so maybe a quick answer, and then we'll log off.
Okay. Yeah. FE plus noise, CTD. Continued maybe? Yes, I thought about linear. Why linear? Okay, so I don't follow the question. So let's dismiss. Yeah, let's take this offline or something.
Okay. All right. Let's thank Shweta again, and we'll reconvene at 9:45. So that's in 9 minutes for Rachel's talk.